Yes, so I am Thanadol.
I'm Nils. Songtao.
Yes, so we're here to present our project, which is RAYSAM.
And you're all from different universities?
All KTH.
We are,
KTH.
we are from KTH, sitting in the same office.
Oh, nice.
Same building.
Same building, not
Same
same
building,
office.
not same office. We are located in Stockholm, signed for library. Is something wrong here?
You may have to click the screen and then.
That's the. Yes, so we have the GitHub page here. You can follow from the link in Canvas. So it's RAYSAM, including everything, all the details. It guides you how to download the dataset and how you start training. There's some even other. So what we're going to talk today, we start from SAM and microsam. Then we talk about the dataset where we get it from the Human Protein Atlas. And you will give the introduction to RAYSAM, then how we can integrate RAYSAM to our code base. I will show some results, and we're going to look at the outlook of what would be the continuation of this project. So I think the first group have mentioned about SAM. So it's basically the model designed by the Meta Facebook team. So ideally, they want to define what can be the foundation model for segmentation, and they want it to be zero-shot generalization, meaning that you don't need anything at all. You just throw in the images, and then they will do segmentation for you. So they first want to define the task, what they want it to be, and they want it to be the promptable. So you can do many things. You can just throw in the image, you can click at the objects, or type some command, for example, cat with black ears, like this. Then the model, then you create the model, and then the model can reiterate the same data set by doing annotation. And from this preprint, eventually they get 1 billion of mass from 11 billion images. There's a guy which named Konstantin Pep. He's sitting in Göttingen. He came up with an idea that, okay, that is a very generalized model for any kind of images. There are a lot of microscopic images, and can we just start fine-tuning based on those images? So he came up with a tool called microsam, which is stand for basically microscopic images per sample. The performance is much better because it's now trained with the microscopy dataset, including electron microscopy, light microscopies. It's speed up annotation, which usually takes a lot of time and a lot of human power, brute force, freaking drawings like a kindergarten. It's so versatile across different types and tools in microscopies. So then when we start these projects, we came up, okay, what can be a good data set for us? We now have a lot of the tools that we want to implement, but what can we make the most out of it? And as we are sitting assigned for Life Laboratory, which is the same place where the Human Protein Atlas are located, I don't believe that any of you have heard about it, but it's the second most visited biological database in the world. Started in Sweden for 25 years. They got funded by the Wallenberg as always as well. So from the first year, they started by producing with a lot of antibodies. So by having the antibodies in the beginning, you can do a lot of things. Now, the project is covering a lot of tools in molecular life science, next-generation sequencing, single-cell RNA-seq, mass spectrometry, proximity central assay, and for imaging, there's the main image from immunohistochemistry, and the second one would be immunofluorescences. So I went to the IT team in the Human Protein Atlas and asked them whether they have any images that we can use in these projects. They got a lot actually, because it's the It's the second most visited database in life science, but they got the most images in life science. Unfortunately, the problem was there was no mask with the dataset, but we somehow managed to get 50 images with segmentation in the end. And that's how we use the data to process these processes.
Before I continue here, in addition to this, what Thanadol just said, they have a lot of segmentation in the Human Protein Atlas, but this is just based on watershed segmentation, and it's not very accurate. And we'll come back to this at the end in the outlook, how this can also be applied to extend this Human Protein Atlas. So keep this in mind. I'll give a quick introduction to Ray. It's an open source framework that we used in our project to scale the training of this SAM model, fine-tuning of SAM. Ray is based on, has 3 different layers. One that is directly interacting with the cluster. And then we have the Ray AI libraries that is a very high level library for users to call. And then we have Ray in between that is communicating between those. Yes. So these AI libraries, this very easy to use API in Python, which you can use to scale your model from single model training from single machines to huge clusters. And it also has a built-in fault tolerance here, and this is because of the Ray core that is included. So the Ray core is an API that allows us to code this in Python, a native Python environment, and communicate through the cluster. Ray is originally written in C++, but we don't need to use any of this in Python here because of this translation, let's call it like this API. And it also supports low-level distributed task scheduling and execution. So you can you have different levels. You can use these AI libraries directly, but you can also go very deep and do everything manually if you want to. It also has a very dynamic resource scaling and efficient utilization. So you can also, similar to FedN, you can include different hardwares here as well. Ray supports both parallel and distributed learning. So in case when the model fits in one GPU, you can you have a big data set, you can just create data shards similar to federated learning. You just distributed or parallel so that you have one model for each worker. But you can also do for very large models. That's not the case here with SAM. It fits in one GPU. With this, it's pretty large encode as a vision transformer, but it's not that large. But if you have larger models, then you can also create model shards and have these distributed models training. Both of this is possible, and this leads to this Ray is very versatile and has a very growing ecosystem. For example, the GPT models were trained using Ray. In this case, the model is larger than GPU size, so you actually have to split it up. And Hugging Face utilizes Ray also for training and scaling models. So it's very, you have a lot of real-world and large-scale AI applications. Probably a lot of these symbols here are familiar to you. Just as a motivation why we wanted to use Ray to go from fine-tuning the SAM model inspired by microsam, and then make an implementation using Ray. So how can you actually create a Ray cluster? Ray cluster consists of a head node and worker nodes, and this is also quite straightforward. For the head node, you just call Ray init, and for the worker node, you also call Ray init, but you connect to this address. So this can either be just auto-connected in the same network. In one cluster, this would work automatically. If you do this with different universities, you need to provide the IP address, so this needs to be public, the IP address. And then you can also connect workers that are distributed over Sweden into one array cluster. What we wanted to do in ScaDaMaLe, we had a Science of Life laboratory where we all working with a Kubernetes cluster, and didn't mention it before, but this lower level, this cloud level, raise pods for different types of clouds, and this, for example, Kubernetes is one of the supported ones. So we were deploying an array cluster on Kubernetes and ScaDaMaLe, but this actually it turned out to be quite tricky because of some security constraints from IT. One reason is that we have a kuberay operator that can auto-scale this training. So you have one head node that stays, but the workers, they can be dynamically deployed and closed again, depending on model training. And so this is basically an autonomous admin in the cluster that can delete and start new jobs, and that's not so appreciated by IT, as you can imagine. So one thing that we did is we have different namespaces, like different user groups in the cluster. You can restrict this to a single user group, but still it came with a lot of difficulties. In the end, we managed to deploy this. We also have a documentation how you can do this. Same if you happen to have a Kubernetes cluster, you can also simulate one on your machines. It's part of the repository. In the end, we didn't train our model here, instead on some local array cluster, as we show here, because currently we only have one GPU in our namespace. We can't connect to different namespaces, and then it didn't make sense. We trained the model on our workstations. We had multiple GPUs there. Just bringing it to the cluster with one GPU didn't make sense, but it would theoretically be possible. And it just demonstrates that it's scalable. And now Jim will continue to explain how we integrated Ray in the
Yes. When it comes to the code, this is where we got our hands dirty. So as mentioned before, our project is based on the public repos microsam as well as Torch-EM. And to be able to integrate Ray, we need to modify them because it's not their problem, but they wrote their code in a very abstract way. It's like trainers over trainers, subclasses, and everything. And some are actually, some of their codes are actually environment specific. So when we want to be scalable, we want to be environment agnostic, we need to modify these codes. And here are some examples or some main codes in our code base. We had a Docker file which can be run theoretically on basically every machine. And also a Conda environment for people who want to use Anaconda or something like that. And we have demos. And this is our main work lies in this microsam Ray, which is a modified microsam repo. And then also this repository uses this Torch-EM, which defines all the data loaders, model trainers, and stuff like that, which we also needed to modify to be able to achieve this, to be able to integrate Ray. And these are the core components of our code base. And the key features is that what we have achieved here is this microscope. Okay, we adapt these codes to our data sets and data types. And we also achieve these environment agnostic configurations. And most importantly, we achieved Ray powered scalable training. So when it comes to technicality, we have these three main parts in our implementation. First is, of course, the main part is the segmentation pipeline, which involves pre-processing of the data. We did some minimum required processing, including the loading, normalization, and stuff like that. Just typical stuff in deep learning, in medical and image processing. And the most important part here is the segmentation part, which utilizes the modified microsam or microsam ray for microscopy image segmentation. This is where it's very easy to summarize our work in a nutshell. Is that we modified the code, but there was a lot of work to do. They have, for example, in this microsam original repo, they define this joint SAM trainer, which is a torch module class, and then it's actually a subclass of base trainer they define somewhere else in their code. And this base trainer is actually a subclass of another base trainer in torch EM. And these trainers are not just something we can use take for granted, because they did it in a very creative way that you input your desired epochs on the stuff like other hyperparameters and take care of everything. But what we want to do is that we don't want it to take care of everything, because it will assign GPUs and stuff like that. But we want Ray to take care of these things. So that is what we spend most of our times on. And also we have some processing to show some visualizations afterward. And also this, when it comes to the Ray part, as mentioned before, using Ray, it enables efficient distributed training, which is scalable. And also we tested this scalability on one local machine with one GPU, with no GPUs. One local machine with multiple GPUs, and also we tested on multiple machines with multiple GPUs, of course. So to show that, okay, our code is actually scalable. And then, during that process, we all showed that the codes can be deployed with our user-friendly configurations. So the benefit of our project is, of course, first and foremost, we prove scalability of handling this specific type of data. Of course, it can be extended to medical data, for example. And also, when it's scalable, it comes naturally with high efficiency. You can reduce processing time with more computational resource and stuff. What we supposed, and we assume that there will be another benefit on accuracy, on performance, but it's something we haven't done in this project, because we show more about from a 0 to 1 process instead of tuning the performance, which can be done in the future if we had the time or anyone else are interested. And then we also, another work can be done in this project is to develop a user-friendly interface. For now, Ray itself provides a very nice interface, but then when it comes to our own data type, it's still to be shown how to use their interface to visualize, for example, our data and our results. And last but not least is the code refactoring. We had some mess in the code. The code achieves its functionalities for sure, but it's still a mess and can be improved in the future. But for now, we just leave it there and want to show you some results for reference. Okay.
So here's our results, and the first is we created a reproducible workflow and to make it easy to use. Everyone wants reproduce can follow. We provide a tutorial in the README file, and so users can read the file and follow the tutorial. And here's the workflow, and we create a Docker file, and the user can build the Docker image according to the Docker file, but also we provide Docker images in GitHub, and we created a workflow in GitHub in the GitHub and in the workflow of actions. It will automatically build and publish the Docker image according to the Docker file, and the user can just download from our GitHub repository. And yeah, here's the link, and yeah, if you can get our slides, you can feel free to click the link and yeah, try it. And yeah, and yeah, also here's a Docker container. Yeah, you can create a Docker container, build or deploy our Docker image on the local machine. We deployed it on a workstation with 2 GPUs, and also when the Docker container can be linked to a local directory in the workstation, so that we can save the results, the code, yeah, in the local directory. So every time when we restart the Docker container or rebuild the Docker image, we won't lose the data and the code. And so it's here. So here's so we have workflow, and we can start training, and yeah, the MicroSam GitHub repository provide a example code for this tutorial, yeah, to tell us how to download the data and fine-tune the model, and yeah, to get some detection results, but it's without ray. So it's we overwrite the whole code and use some part of their code set. So there's you can see the data is it's called a bright field image. Yeah, so which is this is a cancer cell in the cancer cell sample, and it's illuminated by the bright lights. So it's a bright field image, and here's a mask, a ground truth mask. So yeah, we download the data and fine-tune the model with our RAYSAM, and so we get the model, and we use the test image to get the segmentation results. And this is just for verify our code works. So yeah, but it's not the data set we going to use. So, and yeah, here's our human protein atlas image data set. So yeah, we don't have example code, so we write the code to download the data set, and yeah, in the data set it's a fluorescent labeled cells. So as Thanadol mentioned, you have antibody on the antibody, they have fluorescence, and yeah, when you put the antibody, yeah, with the cell, it will bind to some cell structures. So the cell will have some fluorescence, and also we have yeah, ground truth mask. So we download data, fine-tune the model, and get the model, and yeah, we can get some fine-tune results. So it's some other cell images, and here's the segmentation results. So now, so it's what's the results looks like, and okay, here's the metrics. So during the training and the working way, train the model on local machine with 100 epochs, and here's the train loss and the validation loss. It's like it's done. It just looks like it's working, and the yeah, loss is increasing, and here is the IOU. This is yeah, the bonding. Yeah, if you don't know what is IOU, is when you have a segmentation results, you can create a bounding box, and you can compare with the overlap between the ground truth and the predictions bounding box. So you can calculate the IOU according to the overlap. How many overlap? The more overlap, the better the results. So it looks so you can see the during the training the IOU is going. Okay. So here's a summary, and what we have completed is we successfully modified the Python packages RAYSAM and the Touch-M to make them compatible with Ray, and we make them work with Ray, and we also developed a model fine-tuning workflow using Docker, and also we achieved the segment anything model fine-tuning with the human protein atlas dataset we found, and the trend is on a local server. So about the next steps, maybe.
Yeah. So as I already mentioned before, we have the training on Kubernetes theoretically working. We just need more resources. So in the process of applying for them, and then we can more or less easily scale this up also to more GPUs and larger training, longer training. With the 50 images that we have at the moment, that's not necessary. But as Thanadol mentioned at the very beginning, with the way how SAM was trained with this 1 billion mask, that's not what they all annotated manually. But they started with something small and then trained a model based on this. Maybe they didn't train with 50s, but they started at some point, fine-tuned the model, made prediction, had humans correct this, and then update the data set and iteratively create a larger data set. So in the end, what you get is two results. We have one fine-tuned model. In case they have this SAM, segment anything model. In our case, we'll have a fine-tuned for microscopy based on micro-SAM architecture. And but we also have a huge data set in this segment anything, this 1 billion mask. I'm not sure if we can aim for this scale, but at least for the human protein atlas, how many images do you have?
120,000.
120,000 microscopy images. That's already too much for a human to annotate. And then you have a lot of different cells in there. So we can expand the human protein atlas segmentation, which is currently very minimal. These segmentations in biology can also help to analyze these biological data further, because you can imagine it gives any analysis understanding of individuals instead of the group. So that's would be pretty important and pretty useful for analysis here. That's the next step that we can do. Is Thanadol and I both are working on something where we could maybe continue this as part of our PhD projects as related topics here. I think you're working with medical images, so that's the Ray is also scalable for the data loading, as we said. Medical images are usually way larger, so that could also be implemented there. And segmentation medical images is obviously also important. So also some not personal but work or personal interest here to maybe continue this. Thanks for listening.
Yeah, very curious about the Docker pattern. You used to state the state of your training procedure, or what have you put in that Docker image?
The Docker image just contains the environment. I think what you mentioned is just mounting, so you just save it to disk, and everything that happens in the Docker is saved to disk.
Yeah, the data and the code is saved in your local directory. So yes, when you start a Docker, so it's a Docker container, you can link it with your local environment. So it will use the running environment in the Docker container, but also the data can be saved.
Maybe I stepped through it, but did you somehow try to run it on more than one? Like,
Yes.
Yeah.
We actually tested on multiple scenarios, including single node, multiple GPUs, and multiple nodes, multiple GPUs.
Okay.
And they actually went through all the tests. And then, but then in the final stage, when we actually train our final model to the data with the data we have, we use a single machine, but with the same code.
okay, but
I mean, I'm super curious if, I mean, you can get access to Berzelius, given and Chirping with huge resources from the Wallenberg family. I know they have some constraints, like you can't use Docker, but something else like Selenium, or I can't remember now. Can use that. Yeah. So I'm wondering, like, if my guess is people are already using Ray there.
No, not that I know. But we are working on some autoscaler that is not. The autoscaler is the powerful part here.
Okay.
So that that could automatically spin up or submit jobs, then spin up a worker to do this. You could also do this static, so that you say, okay, now I ask for 10 workers, and then manually or write a script to start workers there, and then just start training. It would
Just
also
fix
work.
the budget so that it's compatible.
Yeah. That would work. Yeah. We have something primitive working.
So my next question is this human atlas thingy. So there is no automatic segmenter available for this project yet.
They did the watershed probably 12 years ago, and it's super random. Just like,
So it's not very good.
Yeah, there are lots of algorithms to do some automatic segmentation, but as they mentioned, it's a threshold.
Okay.
I think the main problem there is that because it's a human protein atlas, so you have cells, almost every cell type of the human body. They have different shapes, different sizes. And then if you use something simple like a unit, it's very susceptible for size or shape. And then you would need to have segmentation models for many different segmentation models for subsets of this. That's why a foundation model would be powerful here, but it hasn't been applied to microscopy image. Like life science is always lacking a bit behind in this.
And so my last question is, suppose you get access to something like Berzelius or whatever, and you want to take all your available training data and also custom query data. I mean, one natural way people do this in Ray that I know of is to typically use Spark, for example, or something like this to do all of the data pre-processing and having it in a distributed store ready for Ray to turn into on. Have you thought about how you would use a similar architecture combining Spark and Ray, or because these are huge numbers of files?
Yeah. No, we have not thought about that.
But that would be the data processing part.
Yeah, right. I mean, because
And we in this project we focus more on the model training.
But Ray, do you know why they chose Spark for data preprocessing?
I mean, I don't know. But so Ray is supposed to interoperate with many things, including Flink and Spark and so on. And I just know various talks I've seen where people use that kind of architecture. It's partly because a lot of people already know Spark and some know Ray, and it's mainly a team thing, but also technically it seems more natural anyway.
I think the processing is also quite simple in this case, especially when you try to train foundation models. You don't want to normalize everything to the same, but you want it to be able to also be agnostic a bit to different microscope settings, different lighting, and so on. I don't know if there's so much pre-processing needed. But
generally, like you want some kind of distributed file store for the files because it's too much data. So,
yes. Can I just ask you, like concretely, when you submit a job to Ray,
what do you specify? Do you specify like how many machines you want, and then just point a script, or
Yeah, so Array has some decorators, like I think it's @ray.remote, and then you create a function or classes into remotely runnable class or function, and there you can specify how many GPUs. Like if you would submit a Slurm job, you would say I need so many GPUs, this runtime, and so on. Runtime is not a thing here, but the resources can be specified. If you don't do this, they will automatically calculate it, but can lead to killing this job. Ray is really like also using jobs in queuing system there. So you can submit multiple, like, train this, and will schedule with the available resources. And the more accurate you specify them when submitting, the smoother it runs, or the better this scheduling can happen. Otherwise, it will find a way that maybe something dies, and then you just restart again. It can do this, but it maybe not so smooth.
And is it typically one big job, or can you chain like multiple steps together to form like a bigger job?
Many different. You can do one big. You can many different small ones. You can also say I want half a GPU for this, or I want. So you can share resources there. It's pretty cool.
I mean, also like Ray.io is like, it is founded by the same. So Mate Zaharia is the CTO of Databricks, which is the commercial arm of Apache Spark, right? But his advisor was Ian Stoica, Berkeley, right? Ian Stoica also, Nakamura, I think, PhD student, started Anyscale, which is the commercial arm of Ray.io. So at least in my world, it's like, everything he wanted to do with Spark, but couldn't. Because the primitives are really elegant. Like, in fact, at least all the mathematics you learned in Reza's course is applicable to both systems, but the primitives Ray uses are very different, right? Res promises doesn't have the same kind of directed acyclic graph, whatever the lineage graph in Spark for fault tolerance. It has different things.
Yeah, I think if I'm not mistaken, everything that you we add this Ray decorator, it becomes an asynchronous function. And again, we'll stop and start and continue. So that's why you can run multiple jobs at the same, and they can, depending if there's some waiting time, the others continues.
Yeah, that's good. There are no other questions. Let's thank them again.